Very good morning to all of you. Today I want to start module 3 of session 2. Title of module 3 is Stability of Slopes. Okay. Course outcome of stability of slopes is ability to estimate factor of safety against failure of slopes. Title of subject is Applied Geotechnical Engineering and subject code is 18CV62. It comes in 6 semesters of civil engineering departments. So let us see. This slide explain contents. So today's session 2 is explained in details about these contents. Okay. First point is stability of finite and infinite slopes. To determine stability of finite and infinite slopes. In that, stability of finite slopes, stability of infinite slopes, infinite slope in cohesive soil, infinite slope in cohesionless soil. Stability calculations by method of slices, that is called Swedish methods. These contents are required today. Clear explanations. Okay. Stability of finite and infinite slopes. Okay. Stability of finite slope is explained in details here. A finite slope is one which a base and a top surface, the height being limited. A finite slope is one which a base and a top surface, the height being limited. The inclined faces of earth dams, embankments, excavation and the like are all finite slopes. The inclined faces of earth dams, embankments, excavation and the like are all finite slopes. Thus, the stability analysis of such slopes is of vital importance to be geotechnical engineering profession. Investigation of the stability of finite slopes involves the following steps according to the commonly adopted procedures. So these are the important steps. Assuming a possible slip surface. Next one is studying the equilibrium of the forces acting on this surface. Studying the equilibrium of the forces acting on this surface. And repeating the process until worst slip surface, that is the one with minimum margin of safety is found. So these are the procedures are adopted to investigate stability of finite slopes. Okay, so here possible slip surface, equilibrium of the forces and worst slip surface are important parameters for stability analysis. This slide is explaining in details typical characteristics of the rotational slip in a cohesive soils. Okay, see this sketch. So this is the slope structures, this is ground levels, this is height of the embankments and this is the top width of the embankment. So this structure is constructed that slope in cohesive materials, and this is slip surface of a slope in cohesive materials. How to select? I will explain here. So this dotted line is the embankments, that is slope, and this point is tau, and this is called hue of material at tau. This is okay, and this is called slip circles, this dotted, and this is defined as a torsion, that is a tension crack is nothing but a okay flexible cracks. So this is due to tension crack. Okay, failure of finite slope is cohesive or cohesive frictional soils tends to occur by rotation. The slip surface approximating to the arc of a circle as shown in figure 3.3 below. So this how failure is takes place. So this slip circle is explained to determine the stability of the sloped structures in cohesive soils. Next, the following important methods will be considered for total stress analysis for purely cohesive soil, total stress analysis for cohesive frictional soil. This way this methods of slices. And third one is effective stress analysis for conditions of safety seepage, rapid drawdown, and immediately after constructions. Effective stress analysis by Bishop methods. Next one is friction circle methods and Taylor stability method. So these are the 6 methods are important methods to calculate stability of slope. First one is total stress analysis for purely cohesive soil. Second method is total stress analysis for cohesive frictionless soil, that is C5 soil, that is used by Swedish method of slices. Effective stress analysis for conditions of safety seepage, rapid drawdown, and immediately after constructions, that is effective stress analysis. Fourth method is effective stress analysis by Bishop methods. Fifth method is friction circles methods, and the sixth method is Taylor stability number. So these are the important methods. Let us see stability of infinite slopes, how stability is calculated. How stability is explains in infinite slopes. An infinite slope is one which represents the boundary surface of a semi-infinite soil mass inclined to the horizontal. In practice, if the height of the slope is very large, one may consider it as an infinite one. It is assumed that the soil is homogeneous in its. It is assumed that the soil is homogeneous in its. If different strata are present, the strata boundaries are assumed to be parallel to the surface. Failure tends to occur only along a plane parallel to the surface. The stability analysis for such slopes is relatively simple, and it is dealt with for the cases of purely cohesionless soil, purely cohesive soil, and cohesive frictional soils, that is called C5 soils. The cases in which seepage forces under steady seepage and rapid drawdown occurs are also considered for a purely cohesionless soils. So this diagram is explains for infinite slope in cohesionless soil. So this is horizontal line, this is sloped. Consider this is wedge. Locate this point acting downward. This is weight of the wedge, this is normal force, this is tangential force. And you consider for the resolutions triangular forces. So this as opposite, this as adjacent, this as hypotenuse. So this is self weight acting downward. Okay, this is tensions and this is normals. This is triangle forces for resolution concepts to determine stability. Let us consider an infinite slope in cohesionless soil. Inclination is W. The components of W parallel to and perpendicular to surface of the slope are T we are calculating in terms of W into sin beta, and N, that is normal force, we are calculating W into cos beta respectively. The maximum force restraining the slide acting of T is the shear resistance that could be mobilized by the normal component N's. So in elements of civil engineering, we have already calculated horizontal force Fx equal to W cos theta, and vertical force we are assumed that W sin theta or F sin theta. Same concept is applied here. For cohesionless soil, this is given by N tan phi or W cos beta tan phi, where phi is the angle of internal friction in degree. The factor of safety F against the sliding or failure is given by F equal to restraining force divided by sliding force. Factor of safety F equal to restraining force divided by sliding force is nothing but a restraining force means W cos beta tan beta divided by sliding force means W sin beta. So then now it's become tan phi by tan beta. This is equation 1. For equilibrium, F equal to 1, then tan beta equal to tan phi. Therefore beta equal to phi. Let us see infinite slope in purely cohesive soils. Infinite slope in purely cohesive soils. See, this is embankments. So this is bottom surface of the embankments. Select this is one elemental area of weight is acting downward, that is W, acting at an angle beta, and this is height h. Now locate the normal force, tangential force and shear stress acting at an angle beta. See, this is sigma V, this is force F, self weight is acting downward, then force is acting upwards, and this is normal, the sigma A, this is sigma V. Okay, so based on this concept, here stress strain diagram is plotted here. Along x-axis stress, along y-axis shear stress, sigma tau. See here, this line is plotted at an angle beta, and this line is plotted with respect to C5 value. This line is nothing but a failure plane angle plane, and from this to this has a cohesion C, that is C dash. Now we locate where there is a two lines are concerned. So this is A point, next come towards downward, this is B point, and you select here these 2 points D and F. This is acting at an angle. Measure this as phi dash, this as C. So this diagram is explained for stability analysis of infinite slopes in clay soils. The vertical stress sigma V acting on the plane AB, where sigma V equal to gamma h into cos beta, is represented by OC in figure 5 in the stress diagrams. The normal stress on this plane is OE and shearing stress is EC. The line OC makes an angle beta with the normal axis. The more strength envelope is represented by the line FA, whose equation is tau equal to C plus sigma tan phi. That is FA. Okay, FA line, this lines. Okay, so this line is represented as a tau equal to C plus sigma tan phi. According to the envelope, the shearing strength is ED, where the normal stress is OE. When beta is greater than phi dash, the lines OC and FD meet. From these diagrams I am explaining. In the case the two lines meets at A, okay. In the case the two lines meets at A, so long the shear stress on a plane is less than the failure, figure 5 indicates that at all depths at which the direct stress is less than OB, direct stress is less than OB. Okay, the shearing strength and shearing stress values are equal as represented by AB. So this is AB shearing strength, shearing stress. Failure is imminent. This depth at which the shearing stress and shearing strength are equal is called as critical depth. This depth at which the shearing stress and shearing strength are equal is called as critical depth. Now let us see stability calculations by method of slices, or it is also called as Swedish methods. This slide is explains based on Swedish methods or stability calculation by method of slices. Procedure. So here this diagram is explained in details how to calculate stability analysis. Draw the embankment with respect to given data, that is slope, radius, etc. So means here, now I will explain here. First you draw the horizontal line, then you locate the slope, then you measure the height h and select according to scale these two lines. So bottom line and top line is drawn, and this slope is you select at an angle given. Okay, then after plotting the embankments based on the slope, and now you select the radius. Okay, you select the O point with respect to R radius, then O as a center and draw the circles, that is slip circles, that is OR, O to this point. So this is radius R, and draw the more circle, that is slip circles. Okay, after plotting the slip circle, now measure the total width. So from now draw this, from this point you draw the exact horizontal line, and from this point you measure the total width B. Then you divide number of circles, that is each slices. Maximum is 8. Suppose from here to here is total width is 10 centimeter, you divide it by 8 number of slices. Okay, so from here to first slice, second slice, third slice, fourth slice, fifth, up to maximum is 8 slice. These each slice width equal B. Here B, this is B, this is B, this is B, this is B, means this B is equals total length divided by number of slices. So here is 1, 2, 3, 4, 5, 6. 6 slices are selected. After dividing each slice width, now you select the center of each slices, that is B by 2. Now you locate the W1 points, that is self weight of slice is always acting at the center of each slices. So from this also at the center of slice, this is W2. From this slice you select center, so this is W3. From this slice you select at the center, this is W4. This is W5, this is W6. Okay. After selecting the self weight downward from each center of the slices, now you locate the normal stress passing through these points from O. Draw this line, draw this line, draw this line, draw these lines, from O these lines, from O these lines. So these are you locate as a N1, N2, N3, N4, N5, N6, etc. up to number of slices, how much you have selected. Then after locating a normal stress and self weight, now you locate the tangential force, that is this T1 is perpendicular to this T2 is perpendicular to this. By using protractor you adjust and you locate the tangential points. Now for this you locate T3, next T4, T5, T6 like. After locating tangential force, now you measure the each slices angles, that is theta 1, theta 2, theta 3, theta 4, theta 5, etc. up to number of slices. Okay. So this is the how to plot the embankment with slices, how to divide and how to locate the normal stress, tangential stress and self weights. This is the first step. And in second step, draw the slip circle with a radius R from origins. So it is already okay. Next, now divide the slices at equal width B, and these slices may be limited to 8 maximum numbers. So that's I have already explained. Now locate the center lines of weight W in each slices and join the radius line to each slice center at slip circles from origin O. So that's also I have already explained. Next step, now locate the triangle of each slip circles, that is normal force N and tangential force T. So that is N you calculate, that is normal force equal to W cos theta. This is equation 1. Positive towards clockwise directions. Tangential force T equal to W sin theta. So this is equation 2. And positive towards clockwise directions. So here positive negative is also important. Clockwise positive, anti-clockwise negative. Where W is gamma BH. This is equation number 3. So weight, how we are calculating? Density of soil into area of each slice. Gamma into B into H. Where gamma is unit weight of soil in kilonewton per cubic meter. B is width of each slice in meters. Width of each slice in meters. And H is depth of each slice in meters. So from this slice, say for example this slice, this is first slice, P is width, height is this height plus this one. So this plus this divided by 2, average heights. So for second slice, this height plus this height divided by 2, average height we are getting. Okay, so like that you calculate H. Then next step, now make the tabular column for calculation of sigma n and sigma t. Now make the tabular column for calculation of total normal force and total tangential force. That is, this is the tables. First column is serial number, second column area in meter square, that is we are calculating B into H, weight of each slice weight W in kilonewtons, normal components N in kilonewtons is W cos theta, and tangential components T is calculated by W sin theta. So here theta we are calculating from each slice, W is these columns. Okay, so like this serial number means number of slices. So after calculation of area, weight, normal force, tangential force, you do the summations. Sigma n equal to total force in kilonewton. You do the summation of sigma t, we are getting in kilonewtons. Next step, calculate sliding moments. Calculate sliding moment equal to radius into sigma t. Calculate restoring moments, that is R into CL plus sigma n tan phi. Next step, calculate L equal to R into theta, length of the arc, L equal to R into theta. So here theta in radians, so that is theta value means this value, so this is the theta value. Okay, don't take this, so this theta value. Okay, so this is theta value. So this theta you convert in radians, that is theta into pi by 180, we are getting in radians, multiply R, we are getting length of arc, this. So this total slip circle is L value. Then calculate factor of safety, that is factor of safety equal to restoring moment divided by sliding moments. So here restoring moment meant R times CL plus sigma n tan phi divided by sliding moment means R into sigma t. So here R is cancelled, now it's become CL plus sigma n tan phi divided by sigma t. So that is in number, we are getting factor of safety in numbers. This Swedish method of slices is a general approach which is equally applicable to homogeneous soils, stratified deposits, particularly submerged cases and non-uniform slopes. Seepage effects can be considered. So this Swedish method is also good methods to calculate stability analysis for the given dimensions. Next method is stability calculation by Fellenius methods. Stability calculation by Fellenius methods. Next method is, so there are some disturbance occurs, so due to power connections. Okay, let us see second methods, stability calculations by Felinius methods. Okay, how to calculate stability in terms of factor of safety? See, follow the steps. First step, draw the embankment as per given slope or slope angles. Okay, so means you select horizontal lines, you select a point on this line, so then you select slope angles, so this is slope angles from this horizontal line, and locate the inclines, that is slope. Okay, draw the embankment as per given slope or slope angles, like that. So then locate the top width, as given in data. Okay, with respect to h. So now we are getting slope angles. This is top level, this is ground level, and this is slope angles beta. Okay, next, after locating this, now this h you select from a points below. This height is equal to this height. So then from this e point, so this is a, this is e points, so from this point you select 4.5 times h, that is d points, 4.5 times height. So from e you select 4.5 times h, that is total distance. Then you look at d point. From d point you draw this line, passing through O points. But here how this O point is confirmed? Here alpha, beta and alpha A is given, that is direction angle is given. Okay, so after getting the A and B points, after slope and embankment, with respect to B point you select alpha, beta, that is direction angles with respect to B points, and draw this line, and this as a base, and with respect to this you select as a direction angle, that is alpha A. We are getting this line, so this line and this line you join together, somewhere we are getting O points. So then from D you join passing through O points, so this, see this arrow mark. Okay, so then this is the Felinius methods, how to locate the O point. So then after locating O point, so now next step is similar to Swedish method, means from this you select vertical lines, and from A point select vertical line and measure total width. So then divided by 2, we are getting number of circles. So remaining steps are same. Okay, so here see, first step is take total height of embankment h and locate h distance below the ground level as shown in above figures. See this. Okay, from this here, locate the distance, that is 4.5 times h from E to a point D at 4.5 times h. So these points, this 4.5 times h. Next step, now select the direction angles alpha at point A and point B, that is alpha A and A point and alpha B in degree at B points. See here, alpha A from A points, alpha B from B points. Okay, join these two direction angles from A and B points, that is meeting at O. Next step, now draw the locus of centers of critical circles from point at O points, that is this locus of slip circles, that is factor of safety. Okay, repeat this step with respect to different direction angles and draw the trail circles. Now locate minimum factor of safety. So here where there is a minimum factor of safety, that is the actual factor of safety. Now refer the direction angles alpha A in degree and alpha B in degree for centers of critical circles. So now here this table is given for selecting alpha A and alpha B with respect to slope as well as slope angles. So slope is 0.6:1. So these are the slope, these are the slope angle, and these are the direction angles, alpha A, alpha B in degree with respect to slope or with respect to slope angle. Now you select these two angles, direction angles from these tables. Next step, calculate factor of safety, that is Fs equal to resisting moments by driving moments, that is Cl plus sigma n tan phi divided by sigma t. So we are getting factor of safety in numbers, where L is length of the cord, that is 2r sin theta, and C equal to apparent cohesion in kilonewton per meter square is given. Phi is angle of internal friction of soil in degree, this is also given. So now substitute the value in this form, we are getting factor of safety. This method is applicable for a homogeneous C5 soil when the soil is purely cohesive and homogeneous. The direction angles given in table above directly gives the centers for the most dangerous critical circles. So this is the explanation for Fellinius methods, how to locate the critical slip circles. These are the references are referred for session 2 of module 3 to cover